Good morning, boys and girls. It's actually dead of night, actually around 9:30. So let's talk about the fundamental theorem of calculus, the one that you don't remember, okay? So what it is I'm just going to do one that we actually can figure out the answer to because you'll see the pattern like that, okay? Let's say that I had, let's go from 17 up to x, okay? And then let's say that it is 2x minus cosine x. Oh, that should be t's, shouldn't it? I shouldn't use the same variable. 2t cosine t dt. Okay, and then let's say that I need to take, this is a function, right? It's an integral function. As x changes, this integral would change, right? Because the area would be slightly different each time as you make your x be bigger and bigger and bigger, or smaller for that matter. So it is a function. As x changes, so will the integral, right? So how fast does it change? What's its rate of change? Well, you get that by taking its derivative, right? So the derivative with respect to x, and we could figure out what that equals. There's, like I said, a super pattern, but let's do it one step at a time, okay? Let's see what this actually equals, and then we'll take the derivative, okay? So I'm just gonna, do the fundamental theorem. Let's integrate this. That would be t squared. This would be minus sine t, right? And then we're integrating from 17 to x. These equal each other, right? If I did it right. So then I plug in the x, so I'll have x squared minus sine x, and then I subtract, plug that in, so I'll have 17 squared minus sine 17, Shazam, right? And then this should be the same as this, should be the same as this, if I did it right. Agreed? Okay. Because here's the thing. I said that I needed to take the derivative of this, and we have no idea what that is because it looks too difficult. But it's arguably just the same as taking the derivative of this guy, which is also kind of hairy looking because I don't know what to do with this thing. But since all three of these are the same, it's also the same as taking the derivative of this, and this is easy for me to take the derivative of. Because check it out. What's the derivative of x squared? Well, it's 2x. What's the derivative of minus sine x? It's minus cosine x. And here's the beautiful thing. What's the derivative of a number? 0. What's the derivative of a number? 0. So you have minus 0, but I might as well just keep it here. Peeps, this is the answer. If you need to take the derivative of this guy, you end up right here. And you should take a quick look because you will see a pattern here. I just took the integrand, and that was the answer. So it can look all fancy and all messy and all hairy, but in the end, whatever your integrand is, that's going to be your answer when you just, what we learned in class was, hey, this upper limit, just plug it in to wherever you see the dummy variable, and that will be your answer. Shazam. That's it. They can give you a couple of curveballs, okay? They could say, oh, okay, you think you're so smart? Well, what if we just swapped these around? Let's say we went from x to 17. Aha, now what do? Well, you can just rewrite that using integral properties. You can just say, oh, well, this is equivalent to 17 and x, and you slap a negative out front of it. Okay? And so then you would just end up with a negative here and a positive there once you did all that stuff, okay? The other thing that they can do that is like, not trivial at first is if they put in an x squared here. Am I going to get in trouble? I'm not sure if I will get in trouble. So let's say now, let me get rid of that. Let's say that they do this, okay? So it's not an x up here, it's a function of x, okay? So let's just see how that plays out. We'll do the same thing. Let's just see what this equals legit. And then we'll see if we can't find the pattern, okay? So let me erase this. And then Why is that blanking out? That should not. Please tell me it's recording. It is. Okay, good. So this would become an x squared. Oh, one other thing. Did you notice it doesn't really matter what this number is? Like this could have been negative 45. It could be 100 zillion, because in the end, it's just going to drop out when you take the derivative, okay? All right. Anyway, so now I have this. So instead of, if when I put in an x squared into t squared, that will be x to the fourth. This will be sine of x squared, and then that'll be the same, right? Okay, I think I did that right. Hopefully I did. So now let's go ahead and take the derivative of these with respect to x, derivative with respect to x, derivative with respect to x. This one I can't take the derivative of because it's too fancy looking. This one I also don't get. But this one I can actually take the derivative of. This is just going to be some chain rule stuff. Do you agree, by the way, that this is still going to go to 0, right? This bottom half, so we don't have to worry about it. So if I take the derivative of this guy, I get 4x cubed. And if I take the derivative of this, I got to do the chain rule. So it'll be minus sine of, oh, sorry. It'll be minus cosine of x squared. That's the derivative of the outside. And then times the derivative of the inside. So times a 2x. And this here is our answer. Okay, let's see if I can't recover this here. That makes sense. So that should have been, yeah. So the pattern here is not as obvious. What you end up doing is you still plug in the top limit here and here. So if I did, I'd have 2x squared minus cosine of x squared. Right, do you see that? If I plug in the top limit into the dummy variables, just like our first pattern was, I get this, right? But one thing, is this the same as this up here? No. The other extra step that you have to do is multiply all of this by the derivative of that guy, okay? It's like a chain rule situation where you sort of like did the derivative of the outside, now you have to take the derivative of the inside. Yeah, I'm being sloppy, but that is sort of it. So if you take the derivative of the inside, you get this. This times the derivative of this is 2x. And then check it out. You can probably do this in your head. Guess what this times this is? Do you see I get 4x cubed? And this times this, can you see I get that? So in general, if you want to be like, see what the pattern is and write it in math, you could say this. Hold on. If you need, this whiteboard is like perfectly sized for these two supports of our bookcase. But if I got off just by a little bit, it flips out. Okay, so here's a general pattern. Let's say you got an integral. Let's say that this is c and then some function of x, okay? And then let's say we're integrating whatever. So the pattern here is this. Put this guy in here, all right? So this will equal f of g of x, all right? Every time we see the dummy variable, we'll put this guy here, okay? And then times the derivative of this guy. If this is an x, what's the derivative of x? It's just 1, so you'd be multiplying by 1, so it wouldn't even matter. That's why I didn't have to worry about it when that was just an x. But if it is an x squared or an e to the x or a sine x or whatever function of x is up here, then you would just take your integrand and then multiply it by the derivative of that guy. And that solves all the problems. So that's probably sufficient. And this is 9 minutes long, and I know that's a hassle. But if we just look at 5A, if I can read it. Let's say that we have the a of x, big A of x, equals integral from 1 to x. Is that what it says? 1 to x. And then it looks really horrible. Cube root of t plus 2. all over the cube root of t dt. Is that right? Yeah. And they need a prime of x. Well, just follow the pattern. Every time you see a dummy variable, you put in the upper limit. So you'll have the cube root of, oops, jeepers. You have the cube root of x plus 2 all over the cube root of x times the derivative of this. But guess what the derivative of x is? It's just 1. So don't even worry about it. This is your answer. Okay? And they all work like that. I hope that helps. Okay, see ya.